Hello everyone, Shahin is here with another lecture. This lecture is about equilibrium of forces in a two-dimensional system. So, system of forces can be considered as a group of vectors, and when a structure is at equilibrium, you expect these forces to present a stable system which doesn't translate or doesn't rotate. So in the previous lecture we went through how forces can be combined together, including summation of forces in two dimension, and also we found about finding the moment of one single force or a system of forces about any arbitrary point or axis of rotation. So the difference between rotation about a point and rotation about an axis was explained. So let's start with a quick review problems on how to calculate the forces about a point or forces about an axis. So for example, let's have a look at this demonstration problem that is taken from Hiebler for 5th edition SI, and just to have a closer look at this problem, it's a review problem in page this is in page 172. Okay, closer look at review problem 3-2. That is a force with a magnitude of 7 kilonewton, which is acting at point A, and we want to replace this as an equivalent force and a couple moment at point C. Alright, so we know that when a force is transformed along the line of action, that doesn't require any adjustment to the force system. So for example, if I do have a just I need to adjust my pen. Bear with me a second. Or now. Alright, so this is the force F, which is sitting on the line of action, right? So you can consider AB as the line of action, and if this force is being transferred anywhere along this line of action, here, or even you bring that here, as long as the line of action doesn't change, as long as the direction doesn't change, the effect would be the same. But what happens if I want to transfer this force from here to, for example, as suggested here, to point C? So in this case, my transformation is not collinear with the line of action, but that is along a vector. So in this case, I can simply transfer the very same force here, that is F, and then the penalty I pay for transferring this force from here to here is a moment. So what is that moment? The moment which is compensating that transformation is equal to, I call this moment about C, that is the vector position vector which defines that transformation. Here that is going to be CA multiplied by the F as a vector. So this is the penalty you pay for simplifying that system or by lumping everything at point C. So you transfer the force here with the same magnitude, same direction, but as a penalty you would add a moment. So in the scalar two-dimensional case, the magnitude can be found by the shortest distance between the line of action and that point of interest. But in the vector sense, you just write this as a vector. Alright, so let's start with writing F as a vector. I know that the F is magnitude of F, which is 7 kilonewton, multiplied by the unit vector of F. And unit vector of F, we borrow that from the unit vector of AB. Both of them are sharing the same unit vector, so this is going to be 7 multiplied by unit vector of AB, which is 7 times unit vector of B, that is AB, as a vector divided by the magnitude of AB. So let's do this. To go from A to B, that's the definition of vector B, you have to travel vertically 6 meters in the direction of minus K. So AB is minus 6K, and then you have to travel along positive X by 2 meters plus 2I, and finally you have to travel 3 meters along positive J. And then the magnitude of AB, that is square value of 636 plus a square of 24, a square of 39. So that is equal to 7. So therefore the unit vector of AB can be written as if I organize that one, this is 7 multiplied by 2 by 7 I, and then plus 3 by 7 J minus 6 by 7 K, and that 7 cancels here, so therefore F can be written as 2I plus 3J minus 6K. Now we have force as a vector. The next is you have to write CA as a vector. So CA as a vector, you want to go from C to A, and CA as a vector, I travel, let's choose a different color. So I am going from here to here. That is 2 meters plus 6 meters, which is 6 meters in the positive I plus in the J direction, sorry, J, and then followed by plus 6 in the K direction. And there is no movement in the X direction, so you write this as a 0 I. Now this can be calculated by writing the determinants of forces I, J, K. That's the definition of cross product by 3 by 3 determinant. So the second row would be the component of CA, which are 0 for I, 6 for J, and 6 for K. The third row are the component of F, which we found them to be 2, 3 and minus 6. So if you calculate that, this would be your vector of bending moment, and we already specified F, or we identified F as a 2i plus 3j minus 6k. So now that system, one force acting at the end of rod CA, is identical to the very same system. In this case, everything has been lumped at point C. So point C has F and point C has M. Of course, M includes rotation about all three axes, so you can simply solve that determinant, or you can use a closed form formula if you are rusty with algebra, with the matrices and determinants. So that was a review question. Alright, so now the main topic for today is you want to understand the free body diagram. So that's the main part of this lecture today. What is a free body diagram? A free body diagram is a system including one or more rigid bodies. But this one or more rigid body, the system, should be freed from the universe. So let me give you an example. Here I have one rigid body, the bar, one rigid body, the cable, with that geometry. So this structure is confined to the universe, first at point A, second at the end of the rope, which is fitted to the B. So if you want a free body diagram, you have to release this from universe. So I have to isolate this. So to isolate, just let me bring this into a page where we can explain this easier. That is preliminary problem 4-1 part A from Hibbeler. So that problem, you want to generate a free body diagram from that system. So how do I free this? First of all, you find the type of the confinement. The confinement at A is a hinge. You know, the hinge, what it does is it prevents the beam from movement in two directions. We are talking about the 2D system. So that is point A, this is point B. So I'm trying to make a free body diagram. My free body diagram is a closed enclosure. So anything inside this closed enclosure freed from the universe, or when you open up the constraint, that included all confining forces and external forces. That is your free body diagram. So why do we want a free body diagram? Because this is a tool of a study what forces are acting on a rigid body system. Alright, so the only external force here is 500 Newton. I would include that 500 Newton exactly 3 meters from point A. And then if I want to open up that confinement or constraint, because this is a hinge, it prevents point A moving in X direction and moving in one direction, Y direction, but it's free to rotate. So therefore, to free that, I have to expose the internal forces which were preventing this from movement. And since I don't know the direction of these forces, I assume they are parallel to my X and Y axis, positive direction. Later on, when we impose the condition of equilibrium and solve, if these assumptions are not proper, you find a negative number, and that reminds you of changing your assumption or amending the direction of the force. Okay, how do I replace that internal force inside the cable? Because in a way I have cut this when I freed this one from the universe. Anything outside is universe, anything inside is my free body diagram. So in another term, I have to cut that cable to free it. But if after cutting, the internal force tension here is not exposed as an external force, then my system won't be representative of the real rigid body. So let me call this one tension B. All right, and we know that the cable can only resist in the axial direction. So that is why I replace this one with the same direction. Now, this is the free body diagram. Later on, we look into how this free body diagram can be solved. But just to give you an introduction, when there is a two-dimensional free body diagram, you have to count the number of unknown. So here one unknown is AX, second is AY, and the third one is TB. The input is 500. That is distributed between all these reaction points. And with the two-dimensional free body diagram, if the number of unknowns are 3, that is equal to the number of constraints we have. So this is the constraints. This is the number of unknown, and if they are equal, this free body diagram is solvable. So that is called statically determinate. Statically determinate. So this free body diagram is statically determinate. All right. The concept of the free body diagram is a little bit difficult to digest. We have to go through many demonstrations and practices before everyone feels comfortable with that. So let's go with this free body diagram. That is preliminary problem 4-1, section D. And again, the intention is we want to solve it, we want to generate the free body diagram, not to solve it. Later on, we learn about how to apply the equilibrium condition to solve the free body diagram. At this stage, we are just trying to understand the free body diagram. Alright, so this free body diagram is only one rigid body, the rigid body of AB. So how can I free this from the universe? So I intend to assume an enclosure. So this is my enclosure. The rigid body inside the enclosure is my free body diagram. Anything outside, including the constraint points or ground, these are attached to the universe. So let me just simplify that shape, and just this shape is simplified by a broken line, and this broken line you want that to be isolated from universe. Okay, I bring it here. That's a broken line. This is point A, this is point B. So point A is a hinge, or that's a pin support. It prevents point A from moving in the Y direction, and it prevents point A from moving in the X direction, but it doesn't prevent this member from rotation. Okay. Point B, that's a contact. So if you try to push this normal to the surface of contact, it would resist. So the direction of reaction is only normal. But if you try to push this tangent to this interface, it won't make any resistance. So there is no second component tangent, but there is one normal to the interface. And that is the rule for contact. So this is a contact support, this is a pin support. What about the external force? So there is only one external force which is acting here. So this is exactly 500 Newton with the same direction. So the direction, instead of giving you the angle, you have been provided by a similar triangle resembling the direction of the force. That's 3, 4, 5, and that is all you need. If you want to calculate sine, cos, tan, or any angle here, that triangle is helpful. So now we are done with the free body diagram. Later on we can come back to solve this, but at this stage it's just we want to generate the free body diagram. Let's go to page 195 from the same, and so we have done maybe the next one we do is F. So distributed forces, we deal with them later on. So what you see in case E and C, these are not the point external load, these are external distributed load. Just to give you an introduction, distributed forces are different forces. They are Newton per meter intensity of the load, not the load itself. So later on we learn how to replace them temporarily by a resultant load such that you can calculate the reactions. But for now we just concentrate on the problem with lump forces or point load. Something like case F, preliminary problem 4-1. So how a free body diagram can be generated for this problem. Alright, so this is the rigid body, one rigid body being confined by a pin and a roller support. So again, to free that rigid body from the ground, you have to open up point B, you have to open up point C, and this is your enclosure. What remains inside the enclosure, the rigid body, that is your free body diagram. So it not only includes the external force, also you have to expose the forces, the confining forces which used to be internal. Now you expose them as a external. That is just to make this system to be equivalent to the free version. So this is the free version, A, C, and B. So external force remain as it is. That is 400 Newton. But because you opened up, you freed that reaction, what used to be an internal force, there was a B acting from ground to the bar, one from bar to here, so action reaction, they were canceling each other as long as they were internal. But when you release or free that, this one of the pairs remains, that can be interpreted as you expose the internal force to external. So that is By. And at C, because that's a pin, you would assume that it would prevent this from vertical movement, horizontal movement. Yes, I know that this horizontal would be canceling the horizontal component of this one, and that both of them cannot be in the same direction. But don't worry, in the more complex problem, you cannot anticipate what the direction of this reaction unknown forces are, and all you can do is just to assume they're both positive. You proceed with imposing the condition, and after solving them, if you find a negative number, you reverse the direction of the force. So that is the free body diagram for this system, 30 degrees. All right. Next demonstration problem, we go to page 196. All right, 196, we have fundamental problem 1-4. 1-4. All right, so here we not only want to generate the free body diagram, also we want to solve it. So this is slightly different. But the first step is, let's understand what it takes making free body diagram for solving it. And I bring that system here. Well, that beam is being confined to the ground at point A and B. And this is being confined by not only a hinge at A, but also a roller over there. So just to, this is the free system or the free body system. That is my enclosure. My enclosure just isolate the beam from its ground, and for that I have to open A, I have to open B. So both of A and B are used to attach this to the universe. So when you free this is why we call this free body diagram, FBD. When you free this, the external forces remain the same. So one issue here is external forces are not only translational forces or forces, but also if there are moments, these are also considered as a external force. So here, because they would produce a tendency for rotation, and that support are responsible to prevent that from happening. So 3 kilonewton meter is here. Just be mindful about the unit. And if you open up A, like usual, because it's the hinge support, we are going to deal with hinge support and roller support in many problems. So not that all supports are of that type, but these are very common one. So AX, AY. And then at B, we do have a vertical reaction only because this is a roller contact. All right, so since we are not solving this in a vector fashion, we are solving this in a two-dimensional scalar fashion. For that reason, if any external force here does not comply with the default coordinate system X and Y, you have to replace that by its component. So this 5 kilonewton can be replaced by a vertical force of 4 kilonewton and a horizontal force of 3 kilonewton. But when you resolve, don't forget you have to get rid of the original because you don't want to count it twice. So now this is equivalent to that, and to solve, what you do is just start counting the number of unknown, 1, 2, 3. So this problem is solvable. All right, so the three conditions you have to impose to this problem, that is net forces in X equal to 0, okay, so this is the first condition we have, which is the balance of the forces in the X direction should be equal to 0. That's an algebraic summation, so you have to add a direction, positive direction. This is your assumption. That is condition 1. And then you have condition 2, which is net forces in Y direction equal to 0. And the third condition is net rotation about any point. When a system is at equilibrium, it doesn't matter which point of rotation you are calculating the rotations. So either through A or B, or actually any point belonging to this two-dimensional space, it should provide a 0 net rotation. So in this case, I might assume net rotation about A equal to 0, and there's a good reason for that. But counterclockwise is usually taken as a positive rotation direction. That is just a reference. You could assume the reverse. It's not going to change your answers. All right, so what is the order of imposing this condition? That actually doesn't matter. If I start with the first one, I see that the only horizontal force here is AX and 3, so that equation is solvable. So that is positive AX plus 3 kilonewton, that is 0, and by solving this you get AX equal to minus 3 kilonewton. So in another word, AX, the real AX, is not from left to right, but that is from right to left, and that is 3 kilonewton. If I try to apply the second condition, in my equation there would be two unknown, AY, BY, and that equation should be postponed until you find at least one of them. So therefore I don't continue with this one. Let us shuffle the order. Instead of doing the second next, we do the third next. So then third, the reason I took this point of rotation, because by this decision the contribution of rotation due to two forces here vanish, they can't contribute toward the rotation, and that somehow simplifies my condition equation. So now what you have to assume is this is a two-dimensional frame. You want to put that on the wall, but only you have got one tack pin. So either you put the tack pin here at A or the tack pin at B. Your system has tendency of rotating about that tack pin. So if I only fix the tack pin here and then push this one down, my poster to the wall would rotate clockwise. If I hold this one stationary, put the tack pin here or center of rotation, and then apply this force upward, my poster is gonna rotate counterclockwise, which is positive. And no matter which point I fix, that rotation is clockwise and that is negative. So in your equation, I didn't include 3 kilonewton in any of the condition 1 or 2 because the nature of this is kilonewton meter. Anything else is kilonewton. So any other rotation effect in this equation, they have the dimension of kilonewton meter. So with that point A being assumed as the center of rotation, the first rotation you have 0 because of AX, 0 because of AY, because they collide at the center of rotation. Also 3 kilonewton, ignoring the width of that beam, that is gonna pass through A. So even 3 kilonewton does not contribute toward the rotation, but 4 kilonewton does. It creates a clockwise rotation, right, downward, with that point being fixed. So this is minus 4 kilonewton. Why minus? Because positive is counterclockwise. Minus 4 kilonewton multiply the length. So the distance between here and there, that is 1.5 meter. And then the next rotation effect is due to the BY. I don't know how much the BY is, but I know that this is gonna make a positive rotation, plus BY, and that is multiplied by 1.5 plus 1.5, which is 3. And finally, I have 3 kilonewton in a negative direction, and that concludes the left-hand side of my equation. I have to set this equal to 0, and then this equation can be simplified as minus 6 minus 3 is minus 9. You take it to the other side is plus 9 divided by 3. So BY is equal to 3 kilonewton positive, which means my assumed direction for BY was correct. So now we managed to find AX, we managed to find BY. And how do I find AY? Well, again, I can write another condition of rotation taking with respect to point B, or I can proceed with that, keeping in mind that BY is not unknown anymore, and that has been identified. So let's try this one next. So first I start with AY, which is positive AY, and then minus 4 kilonewton going down, and BY we found this as 3, and then there is no point load. So this doesn't come into that equation, because this equation everything is Newton, that is not included here. So -4, 3, -1, take it to the other side, so AY becomes positive 1 kilonewton, and that means the assumed direction for AY was correct. Now this free body diagram is solved. AX 3 kilonewton, AY 1 kilonewton, and BY 3 kilonewton. Let's move on to see what we have next. Page 196. Alright, so page 196, and the question we are trying to attempt is 4-2. Alright, 4-2 is a tricky problem. Why this is tricky? Because your free body diagram is not potentially involving one rigid body, but also two rigid bodies. Alright, so here have to be careful. Let's see how does it look like. All right, so one rigid body is the beam, horizontal beam, the other rigid body is CD. But if I try to open AB, I'm going to have a problem, and the problem is, all right, as usual, this is your enclosure, and you have to open up this one from both A and C. But the minute you do that, you realize, okay, that is my external force at point B. A, the internal forces, because this is a hinge, that is AY, AX. And at C, because this is a hinge, if I include two reaction, two resistance, CX, CY, now you realize there is 1, 2, 3, 4 unknown, and you only have 3 conditions. So that is not solvable. How can we solve this? Or if I try to isolate my free body diagram as DC, I have to open up both D and C, and the problem with that is there is 2 problems here. Okay, so that is DC, hinge, hinge, 2 reaction here, 2 reaction here. Not only you have 4 unknown, the other problem is there is no input, so everything is unknown. There is no external force to solve that free body diagram. So we tried this one, that didn't work. So the other alternative is, what if I choose to keep 2 members together in my free body diagram and only open up A and D? That's not gonna solve the problem either, because again, now there will be 1, 2, 3, 4 reactions, 4 unknown, and only 3 conditions. So we tried this free body diagram, this free body diagram, this free body diagram. None of them seems to be solvable. So that is what makes this problem challenging. And now the solution to this problem is, you have to notice DC is a 2-force member. DC being a 2-force member, it means when you are making the free body diagram, a 2-force member, doesn't matter if that's a straight or that is a boomerang shape, as long as this is 2-force member, it can only be at equilibrium if the line of action of the forces are like so. Any other directional, that would not keep this one preventing from rotation. A 2-force member can only take the 2 forces along its center line. So the center line for a boomerang is the line of action for the forces like so. With this one, the line of action will be like this, and that is telling me look, this free body diagram, go back and fix it. So instead of putting two reaction here, with that free body diagram, the way to solve this is assume FCD in axis of CD and FCD like this in that axis, right? All right. So, but this free body diagram, again, because this doesn't have any input, I can transfer this internal force here, but instead of putting Cx, Cy, this time instead of putting Cx, Cy, I only include the external force in the direction of that FCD. But the good news is I already know the direction of this force. So this is 1.5, 1.5. This angle is 45 degrees. So this force, the direction I know, only the magnitude becomes unknown, 45 degrees. So now this free body diagram is solvable. 1 unknown, 2 unknown, 3 unknown, and that problem is solvable. Even if I go with the free body diagram including two members together, so the lower hinge, you would replace these two forces by one single force of FCD. So either you go with that free body diagram or this free body diagram, both of them are solvable. So let's keep it limited to one single rigid body as AB and try to solve that. Alright, so how do we go about solving that? Like usual, there are three conditions to apply. Let's start with condition of rotation. Well, before going to that external force, it does not comply with my default coordinate system X and Y, so I would prefer to replace this by its orthogonal component rather itself. So I would break that into FCD multiplied by cos sine 45, which is 0.707, and also a horizontal component which is also equal to 0.707 FCD. And in that you have to get rid of the force which has been consumed and resolved in two forces. So this free body diagram is similar to the previous one, but the difference is now all forces are in X and Y coordinate. So let's try the condition of rotation about A. So the condition, we have net forces in X equal to 0, condition 1, net forces in Y equal to 0, positive, and net rotation, I would take my rotation with respect to point A. Why point A? Because taking net rotation with respect to point A, I don't have to worry about two unknowns to begin with, and it only leaves me with one active unknown in my rotation equation condition, and that is easily solvable. Alright, so no special order to apply this condition. I prefer to apply condition 3 first. So what do I mean by net rotation, net forces? What this should go to the left hand side of the equation. That is any rotational effect which are here, they should be written in an algebraic positive negative on the left hand side, and on the right hand side the 0 indicates that all these net rotation effects, they can only cancel each other to 0 rotation. That is a condition for stability of the system. So if I want to apply that, this is net rotation with respect to A, that is the positive direction. So none of these two forces contribute toward the rotation, but this one does. Is 0.707 FCD, and the direction of the rotation would be clockwise, so that is negative. So I have fixed this point, and that is my frame. Now the frame is not stable. If I pull this down about this point, it makes a clockwise rotation. So that's why I put it as negative into that equation. Next term, that is passing through the center of rotation. This horizontal component does not contribute toward the rotation. And only the remaining one is this end force at B, but it contributes at a negative rotation. So that is 4 kilonewton, and the arm of the shortest distance between that line of action and here, which is the arm of rotation, 1.5 plus 1.5, this is 3. All right, equal to 0. And you find FCD to be something negative. So what does that mean is you have to reverse your assumption. We initially assumed that this force was in tension, but the reality is this force is in compression, and that's not difficult to visualize. When you push this down, that bracket or this link is holding a compressive load, right? So that's the meaning of, you find this almost, the answer is 70 kilonewton, but that 70 kilonewton is not positive, that is negative. And what that means is this member is under compression. So when you're solving for the forces, not only the magnitude, but also in many cases you want to know the nature of the force, whether this is compressive or tensile. All right, now we are in the position to find out AX, because applying the first condition, you have one horizontal force here, one horizontal force here, and that is AX positive minus 707 times FCD is minus 17 equal to 0. So AX becomes minus 12 kilonewton, and that means when you push this one down, AX would try to pull this back. So that's what the meaning of that negative sign is, and that makes sense. You can visualize by pushing this down, this is not resisting forward, it's resisting backward. And now the last, you can apply this condition to find out Fy. So to find out Fy, third condition, so third condition, that is Ay. Ay positive. So FCD multiplied by 0.707, that is plus 12, and then you have a 4 kilonewton here is equal to 0, so therefore Ay is equal to minus 16. So that means Ay is not pushing this up, Ay is pulling this down. And as such, you manage to find out all the reaction by solving the free body diagrams. All right, let's go back to see what we have next. The last one we have is 4-11. That is on page 198. 198 from Hippler and 4-8. So you want to solve this problem. So that's an interesting problem as far as the supports are concerned. So you're using a pipe lever against two concrete blocks, and once you're pulling down the end of the lever, you would like to know how much reactions developed at contact with the concrete. So one interesting thing with this problem is the type of the support. So if I choose my free body diagram enclosed like this, it means my rigid body is the L-shaped pipe, and I have to open up, I have to free this at point A, I have to free this at point B, I have to free this at point C. But when you free them, those contacts should be replaced by external forces, because before free them at A, B, C you did have internal forces, action, reaction. Now you isolate this, you only keep one of the pairs, either the action or reaction. In this case we expose them and pretend these are external forces to make the free body diagram comparable to non-free version. So let's see. The big question is, we know that with the contact support the reaction would be normal, but the question is whether that reaction is normal to the pipe or normal to the concrete. I know that some of you might be able to just figure out the direction, but let's see how systematically this can be found. So let's pretend you don't know whether that reaction is normal to the concrete or normal to the pipe. How can you find out? Or even here, whether the reaction is normal to the concrete, normal to the pipe. It has nothing to do with the concrete or pipe. It has to do with the nature of the contact. So the nature of contact, I mean, if for any reason point A is going to slide, what would be the direction of the sliding? So if forget the friction, sliding would be along the edge of the concrete, right? So because it would slide potentially along the concrete edge, so the reaction is normal to the concrete or normal to the path of sliding. This is the path of sliding. So I'll just make the free body diagram assuming that this is my pipe, right? So this is the bent pipe, and at A, sliding direction is here, normal to that path of sliding is normal to the concrete. So I would add a reaction force which is normal to the direction of sliding, not normal to the pipe. But here the direction of sliding of B is not along the concrete, that is along the pipe. So at point B, that is the sliding direction, and my single normal contact would be normal to the pipe, not normal to the concrete. So I would call this one NA, would call this one NB, and yeah, that's all the challenge we had. And the only thing remaining is the external force 300 Newton here. And now if the pipe weight was significant, you would have included here, but there is no mention of the weight of the pipe. That is not being included in the free body diagram. So all we have to do now is you just assume a coordinate system. It seems there is not a preferred coordinate system as such. So if you decide to keep the coordinate system as horizontal, vertical, which in many cases is the case. By the way, choice of coordinate system should not change your result. The result remains the same. So with this, I need to resolve the forces in the direction like so. So I would replace this one by 300 cos 30. So 300 cos 30 is almost 260. Almost 260. Let's simplify. And then the horizontal component of this force is 300 sine 30, which is 150. And the unit is Newton, but just I'm going to get rid of the original force. This is essential, making sure you don't count the same thing twice. And then NB is aligned the coordinate system, that's okay. How do I break NA into components? So NA, you have to do a bit of trigonometry. So if I draw a vertical line here, this vertical line, that is normal to here, right? So that is 30 degrees, and all right, is this the case that this is 30 degree? Yes, it is, because this side is parallel to here and that side is parallel to here, so that is 30 degree. Let me make this a bit thicker, the thickness of the pen, maybe you can read that better. So this is 30 degrees, and now you can break that force into vertical and horizontal component. That one is NA cos 30, and vertical one is NA sine 30, so this is half NA. And now you remove the original force because that was consumed, it was resolved into two forces. Now let's see if this problem is solvable. Yeah, by the way, I have forgotten to include one reaction here, and at point C the direction of sliding would be along the pipe, so your reaction would be normal to the pipe, not normal to the concrete. So that is NC. So in this problem, you have 1, 2, 3 unknown and 3 conditions. So this problem is solvable. Or how can we start with this problem? I think the best start is imposing the net forces in the direction of x equal to 0, because if I do that, the condition has only one unknown, that is plus 0.867 NA equal to 0, and therefore NA is 150 divided by 30 cosine. Which is 173 almost. Now that I have NA, let's make net rotation about point C. So this is point C, that is point B, and that is point A. So it's not if I apply the net forces in the y direction, in my equation both NC and NB are unknown, and that should be postponed. So I postpone the condition of net forces in y and continue with net rotation about point C. So net rotation about point C equal to 0. What that means is you don't have to worry about this unknown because it won't contribute to other rotation. It vanishes the rotation due to NC. But that one also vanishes. 150 passes through C, but 260 makes a negative rotation. Minus 260 times 0.5 because that's clockwise. And then NB also it contributes into a negative rotation, and the arm of rotation NB is 0.5 NB. And then this would pass above point C, and that makes a negative rotation. But the arm of rotation, this is the line of action for that component, and the distance from here to here is 2.6. So the arm of rotation is 2.6, and the magnitude of this one is cos 30 or 0.867 NA. NA was 173.2, and now the rotation of this was counted. This was counted, horizontal counted. The last one has not been included yet. So this last component, it makes a negative rotation. That's minus 0.5 times NA. NA, what is NA? NA, we found this to be 173.2, and that is the line of action, the shortest distance between center of rotation C and the line of action. That is 0.5 plus 0.15 is multiplied by 0.65. So this should be equal to 0. That equation is solvable. It only has NB as the unknown. So that's minus 130 minus half NB. So this horizontal rotation, it is going above C, and that makes a negative rotation. So let's just find out that number, 0.26 multiplied by cos 30 and that multiplied by 173.2, which is 40 minus 40, and the last term is 0.5 multiplied by 732 multiplied by 0.65. That is minus 56.3. So therefore you combine all this together, and that divided by half, so this is minus 0.5 NB minus okay, just one more time with the sign. 150 passes through C, 260 I think I need to NB is multiplied by So something not quite right with this equation. 260 negative rotation, NB is negative rotation, and both component of NA make a negative rotation also. Okay, net rotation about point C is equal to 0. Yeah, okay, so the problem is that 130 times half, it's not a negative rotation, that's a positive rotation. That's what mistake I made. Sorry about that. Now it makes more sense. So 130 minus 96 minus 96.3, that's 30. So this is equal to minus 33.7, and then your NB is 67.4. 67.4 Newton. Now we managed to find NA, this is NB, and the last one is NC. So to find NC, the condition we apply is net forces in y direction equal to 0. So net forces in y direction equal to 0, that being positive. So you would have minus 260, that's this one, plus NC, and NB we found this to be 60, this is negative 67.4, and last is 0.5 NA in a negative direction, minus 0.5, and NA was 173.2 is equal to 0. And then you get NC is equal to 260 plus 67.4 plus 173.2 by 2. Okay, NC is 414. Okay, and that is you start from this problem with two or T3 contact points, identifying the reactions, directions, making the free body diagram, resolving the forces along the selected x and y coordinate, and then starting to apply the three conditions we have. We have chosen to start with a balance of forces in x direction, that means no translation in x, and then we followed this by condition of net rotation about c to find nb, and finally we applied the third condition, net forces aligned y equal to 0. And that brings this presentation to its end. I hope you find this useful. Take care and have a great day. Bye.